so in this one, we know we have the switch that we're going to have to use. And I'm going to try and draw it using the elements the way they are as much as possible, but the switch is the one that matters the most. So, they've got this thing here, something like that. So when it's in one position, we want to, be charging a capacitor. And when it's in the other position, we want to be discharging the capacitor through another capacitor. So I'm going to put the capacitor that we want to charge and discharge in the middle. And it doesn't indicate that I need to have the resistor in with capacitor 1 when it's charging, but I'm going to put it there anyways, because generally it's bad form to just try and charge a capacitor directly off a battery. We tend to, and this is one of those things that won't be on the exam either, but since there's such a reliance or such a desire to have you guys have laboratory skill, one of the things you may want to kind of write down in your notes is that in real circuits, no matter what, there's going to be some resistance. So if you think you can charge a capacitor directly from a battery, you're wrong. You're still going to be having a time constant. There's going to be resistance in the wires, and there's going to be resistance in the battery itself. So using a resistor or having a resistor in line with your capacitor whenever you're using it makes sense and should be taken into account every time. Oops, I don't want to do that. I want to have the battery in here. So here's my battery. And now there's my charging side. So this is my EMF. Now, the nice thing about this is when the switch is in the left position, I have a single loop that connects the battery, the resistor, and capacitor 1 together. But I also know that the moment I pull the switch away from the left position, the battery, that loop is disconnected. So I'm going to create another loop on the other side with capacitor 2 in it that allow a new loop to be established when the switch is thrown to the other side. It's the next part of the question that I think is a little interesting, which is kind of why I put it up there, because I thought this could be in the vein of how they monitor the AP exam a little bit. It says switch is initially in a position to fully charge capacitor 1 at time equals 0, and the switch is moved to the second position. I'm sorry, at time equals 0, the switch is moved to the second position. So we are throwing the switch onto this side with a fully charged capacitor, and that's going to be time equals 0. The charge as a function of time for both capacitors after the switch is moved is plotted on the graph below. Label each box to indicate the graph corresponding to C1 and C2. So, which capacitor's charge do you think is going to get reduced when we throw the switch? Capacitor 1 or capacitor 2? Yeah, capacitor 1 starts with charge. And although Savri's mic is muted, I did see her mouth the words. So with that being said, yeah, I think capacitor 1 is going to start charged, and it's not going to go to 0. Remember, what's going to happen in this case is when we throw the switch, we're going to reach a condition where no charge will flow in the circuit. And I want you to be able to tell me what condition that has to be. So, I mean, we notice on the graph that capacitor 2 becomes charged, sure. And if we look at the graph itself, and I'll draw this because I can't necessarily assume that you guys have the problem in front of you, but there's this kind of thing going on with a charge here and time here. And we have that graph and that graph. This has got to be C2 and this has got to be C1. But C1 doesn't go to 0, which means capacitor 1 doesn't fully discharge. And I would expect that. I would expect charges to flow until a new equilibrium condition is reached. Now, I'm very interested in knowing if you guys know what that new equilibrium condition will be. Like, how do I know when all the charges have moved from capacitor 1 to capacitor 2 that are going to move under this new circumstance? Can anybody tell me that?
charge is equal to total capacitance of the new circuit? Because now you're adding a second circuit into the loop.
Well, no, because remember, when we pull this switch here, when we take this apart and disconnect the EMF, we are no longer able to transfer any charges from the one side of the capacitor to the other. So the total amount of available charge, I'll say QT, has already been set up. And after a long time, we're going to get Q1 and Q2 here, because the amount of charge is fixed after we release the battery. So QT represents the amount of charge that would have existed if it was just Q1 alone connected to the EMF. But due to conservation of charge, after I throw the switch, the charge is going to redistribute itself in such a way that the total charges on both capacitors has to equal the charge that was on capacitor 1 initially. That's why if you look at this graph, and I didn't do a great job of doing it, this plus this should equal that, which would be QT. I don't know, I drew it great, but that was my attempt. Savri?
Would the distribution of charge be proportional to like the capacitance?
It would. But that still doesn't provide us with what the condition's going to be for it.
Is it like when the current goes to zero because charged particles aren't moving anymore?
That's true. But we need one more piece, something that tells us why the current is zero now. So all these things you're saying are true. Would we all be able to agree that there's going to be a voltage established on this capacitor after a short time as the charges begin to flow? And there's a potential difference on this capacitor as well, right? The charges can no longer flow when the potential on both capacitors is equal, because there's no change in potential between the two capacitors. At t equals 0, the potential difference across capacitor 2 is 0, and the potential difference across capacitor 1 is whatever this EMF is at time equals 0. But after a time, according to our graph, sometime in the future, there's going to be a equalization of these two potentials. And when these two potentials are equal, there will be no charges pushed through that resistor. So that will be the condition where the current goes to 0. And in order to create that condition is when V1 will equal V2. Now, just this screen looks a little bit cumbersome for me. I want to switch it to something else for just a minute, if that's okay with you guys. Because this is a pretty complete question in that it hits all of the notes. Except for dielectrics, it hits all of the notes that I think you need to have. This is our initial circuit. Right. This is our initial circuit. And after a long time, we will establish that this is going to be the total charge on the capacitor. This is going to be the EMF. After it's been connected for a long time, that's what I would expect. So that at time 0, this is when the switch is now thrown and capacitor 1 and capacitor 2 are now in a circuit together. At t equals 0, this still has to be the EMF over here. This still has to be QT on this resistor, and this voltage on V2 is 0, and the charge on capacitor 2 is 0. And then after a long time, and I'm drawing this in 3 phases because I think that there's 3 things that happen. So after a long time, capacitor 1 will have charge Q1 and voltage V1, and capacitor 2 is going to have charge Q2 and voltage V2. Okay, now the reason I'm putting it like this is because we have information that we can now apply to this. We know in the long term, the steady state condition here at the very beginning, we know that the charge in the capacitor, QT, is going to be C1 times the EMF. I'm just using the definition of capacitance, which is Q over V, to tell me what QT will be in terms of our given quantities, because they give us quantities up here. R is 1,000, C1 is 2 microfarads. I'm assuming that we're going to have to use those here in a bit. Now, the moment the switch is thrown, those are the conditions that affect this circuit. So I know how much QT is because I can calculate it. At the same time, in the long term, I know that V1 will have to equal V2. That will have to be true. And I know that QT is going to have to equal Q1 plus Q2. Now, there are a lot of things I can put here. For example, just looking at this, I should be able to say that Q1 over C1 equals Q2 over C2. You guys see why that has to be true? I just took this definition, solved it for V, and then applied it here. Are we okay so far? All right. And I think we can also then say that Q1 plus Q2 is going to equal C1 times the EMF. Now, I kind of want to stop right here because I think I've given you a lot from which to work. We have what appears to be quite a few unknowns, but I think we have fewer unknowns than it looks like. I think that we can probably do some substitution here to maybe isolate Q1 by itself or Q2 by itself. And once we know Q1 or Q2, we can solve the rest of the circuit. But I see two equations with two unknowns. Don't you guys? So does that give you a good start there, Savri? A piece of information here that without it, you couldn't solve this circuit. And that piece was quite simply, if you have multiple capacitors in a circuit, you're going to have a flow of charged particles as long as there's a potential difference. But when there's no longer a potential difference, there's no longer a flow of charged particles. It is that potential difference that drives the flow of charged particles. So as long as the two capacitors weren't at the same potential difference, charges had to flow in order for the potential differences to be the same. That's not just capacitor circuits. That's every circuit ever created. Charges only flow due to the fact that there is a potential difference within the circuit. So anytime two parts of a circuit are brought to the same potential, there's not going to be a flow of charges. We even saw that on the bridge question with the resistors. There's no current across the bridge when the system was brought to the same potential. So, the idea of there being a potential difference in your circuit is the driving force that moves the current. The second thing I want to point out here is we've talked about this kind of before, there's like these fundamental laws of physics, these things that can't be violated. But there are also rules. So this idea of capacitance, this definition, it's not really a rule. It's just how we define what capacitance is. It's a useful feature of this particular electronic device. We know it stores a certain amount of charge when a voltage is applied. Now, as a definition goes, we define capacitance in that way so that we can compare two devices. We can compare how one device will behave compared to another device. That's why we have those definitions. But something like conservation of charge is a higher order property of the universe. It has nothing to do with capacitance. But in any environment where there's going to be a movement of charged particles, you need to be able to kind of assess where those charges have gone. There's a finite number of them. Now, if you have some device that will continuously allow for charges to be separated and moved, that's great. But in a system where the amount of charge you have is finite, you can trace the number of charged particles. You can always count on the fact that there will be a finite number of those particles. They might move from one part of the system to another. For example, if I take a dielectric and try and put it inside one of these capacitors, I can't change the number of charges in the circuit. I can change the behavior of those charges and where they are, but I can't change the number of charges. So putting a dielectric in there affects something about the circuit, but it can't change the total number of charges. So it's things like this that you have to understand. There are these higher order ideas. Capacitance is flexible. It can change. I can add a dielectric and change the capacitance, but I cannot change the number of charges if the system's isolated. It's these things that I think help us, have these higher order ideas, and conservation of charge is a big one. All right, I'm limited on time here. It's like 2 minutes. So is there anything else you guys wanted to ask or that I can do quick? Because, 2 minutes is 2 minutes.